So my name is Anshul Gupta, and yeah, that's the topic of my talk today. So firstly, entropy, as we all know, is a measure of the system's thermal energy that's not available for doing useful work. So we can treat it as lost energy. And in the space industry, whilst our collective potential has never been higher, there is also high loss that prevents this potential from being converted into capability. But to understand that, we need to first analyze the industry as a whole. So firstly, humanity is fundamentally a very curious species. In 2021, we achieved first powered flight on another world with the Ingenuity helicopter on Mars. In 2026, just 2 weeks ago, humanity went beyond low Earth orbit for the first time in 57 years. In the next 2 years, we would like to step foot on the moon again. By the end of the decade, we would like to establish a sustained presence around the moon. By 2040, we would like to achieve first powered flight in the outer solar system. And by the turn of the century, we want to establish a sustained interplanetary presence with multiple space stations and bases across the inner solar system. So it's very clear that humanity is a very ambitious species. And the space industry matches this ambition. So according to McKinsey & Company, the global space industry is projected to reach $1.8 trillion in the next 9 years, which is a threefold increase from $630 billion in 2023. The space economy is expected to grow at 9% per annum, which is almost twice the global economy's growth, which is at 5% per annum. And this 9% is split into two different categories. We have reach and we have backbone. The backbone revenue comes from service providers as well as companies that launch space and operate space hardware, such as SpaceX, NASA, ESA, JAXA, ISRO, SANSA, and many others. And they're valued at $330 billion, and they're growing at 7% per annum. But the reach comprises of value that space tech creates. So because of these satellites, we have GPS, we have 5G, we have e-hailing services, and multiple other services. And this section of the industry is growing at 11% per annum. So the space industry within the next 10 years is no longer going to be just a niche for government agencies. It's going to become ubiquitous across the global economy. Now, not only is this industry obviously generates a lot of interest in both the technical populace and the non-technical populace. For instance, Kerbal Space Program is an industry-leading aerospace simulator that is set in a fictional star system. This game leads the industry, and it's 11 years old. And playing this game effectively requires an intuitive and mathematical grasp of orbital mechanics, delta V budgeting, and multi-stage systems integration. As a result, we could use this game as a high-fidelity proxy for technical supply. After the Artemis II mission, which is highlighted by this blue dot, the launch of the Artemis II mission, concurrent players of this game saw a 300% surge, according to Steam. And this peaked on the 12th of April, about a week ago. This clearly shows that there's a lot of interest in the space industry, especially because this figure, 21,037, was higher than any other time in the game's history. Despite this, there is a mismatch, because according to the AIA, the industry loses up to 15% of its workforce per annum. Now, this mismatch is a bit of a problem because according to the World Economic Forum, accessibility is identified as a primary failure point. And lack of accessibility could lead to a loss of up to $400 billion within the next 9 years. So that $400 billion would come out of the 1.8 trillion estimate. And $400 billion is on the same scale as the GDP of countries like Nigeria and South Africa. So whilst we don't have a shortage anymore of talent, we do need to revamp our human capital pipeline because it's currently an open loop system. If we don't, then in the next 9 years, we will essentially be erasing one country's worth of value of the planet. We now transition from the macro scale to the micro scale, where we examine the situation of the individual experience of a student in high school about to start university and considering what major they would do. Now, I want to talk about something called Miller's Law. Miller's Law states that human working memory has a strict capacity of 7, give or take 2, discrete chunks of information. So for students that are seeing equations like these for the first time, or equations like gravitational field strength or electric field strength, they aren't storing the entire equation as one chunk. They're storing each single variable as a separate chunk. And it's easy to see how with large equations, the 7 chunks of discrete memory fills up very quickly. This leads me to my next point, which is the cognitive load theory. The cognitive load theory describes 3 different types of mental effort. There's intrinsic load, which is the actual difficulty in trying to understand concepts like gravity or geodesics. Then there's extraneous load, which is the energy spent in decoding these symbols, so trying to look at these variables, trying to understand what does that gamma sign mean, what does the second derivative mean, what does x and mu mean. And then there's domain load, which is the useful energy spent building a mental model in our brain. Now, because of this splitting of the equation into multiple different chunks, domain load stays very low, but extraneous load spikes up. So extraneous load can spike up to 56% of total cognitive effort, which would mean that students are spending more time actually just looking at equations and trying to understand what each of the variables mean, as opposed to building a mental model of how the concept works, how gravity works, or how geodesics work. This can create a perception of a much steeper learning curve than is actually the case, and this can cause students to think that astronomy or other STEM fields might not be their cup of tea, even though it very much would be. Another problem I want to talk about is the perception that astronomy, you can't have a job in astronomy for anyone that doesn't have a doctorate. From the perspective of a student that's about to start university, this means that they think that getting into astronomy is a 10-year-long tunnel where you'll only get accepted at the very, very end, and there's no off-ramps. In fact, according to the American Institute of Physics, undergraduate astronomy enrollment may have surged, but permanent research positions remain largely static, which means that data shows that 1 in 10 astronomy PhDs eventually land a permanent faculty or research position. This means that when a student looks at this data, rational choice theory can predict their decision, where some students may want to gravitate away from a field in astronomy itself and probably go to other STEM fields like engineering, maths, physics, computer science, and their goal would be to return to astronomy during masters. But there's another small caveat in that, where core programs in these disciplines are obviously very heavily focused towards their own industries, and as a result, they're optimized for Earth-based industries. And this can create a mismatch between people who want to go to space but are just studying these different disciplines. So by the time a student graduates, the noise of standard industrial recruitment, for instance, fintech or automation or mining, will drown out the original goal of going back into the astronomy sector. And this safe haven of a discipline ends up becoming a talent sink, where we lose a decent portion of our talents too. Now, obviously, I want to talk about how we can try to fix a few of these issues, or at least curb the effects that they have. So research from MIT actually shows that the brain can process images in as little as 13 milliseconds, which is up to 60,000 times faster than text. This is because we use the visual cortex as opposed to the prefrontal cortex of the brain, and the visual cortex can be thought of as a GPU. And the visual cortex has a much higher bandwidth than the prefrontal cortex. And as a result, if we visualize the physics first, it's much easier for the prefrontal cortex to just read an equation and read the math and label basically the mental model the visual cortex has created. And effectively what we've done is reduce the extraneous load greatly and reinvested that energy into germane loads, which means the brain can understand and build a mental model much quicker than it would if we had just presented the equation in front of them. Obviously, this has the implication that it eases the learning curve and reduces the barrier to entry which in turn improves accessibility as the World Economic Forum wanted. Another issue is the mismatch between theory and application. And what do I mean by this? See, there is still the fog around a pathway into a career in astronomy for high school students. And the way to solve this would be a very high resolution industrial simulation. We would use a document called an RFP, which is the backbone of the entire space economy, whether it be telescope mirrors for Hubble or the Artemis lunar landers. RFPs are used everywhere in the industry. And despite how technically literate students may be, it is difficult for students to actually gain exposure to this document until they get into the industry. So to bridge this gap and to better inform students about the disciplines that play a role in the space industry, we can use high fidelity simulations such as space design competitions, a few of which happen in South Africa and internationally as well. This gives them hands-on experience relating to the importance of their skill in the ecosystem, and they can make a much more informed choice. And obviously, they then understand and appreciate the constraints of the industry, so stuff like radiation hardening, or the energy needed to basically get to Earth orbit or get to the moon, and why it's much easier to launch off the moon than off the Earth, for instance. And I'll talk a bit more about these skills, but there is no doubt that simulations like these result in students being upskilled in skills that have massive applications on Earth. But obviously, what is the benefit of upskilling students like this? See, space is an extremely hostile environment. Building tech for space is a stress test for human ingenuity and research. So it proves to be an effective R&D pipeline for tech that has massive applications on Earth. And I'll get to some examples in a minute, but I just want to talk about the return on investment. See, according to NASA's FY 2021 Economic Impact Report, Apollo had a 7-to-1 return on investment. And this $7 is essentially the value added to the GDP of America for every $1 spent on Apollo. This could be NASA paying its contractors, and those contractors paying employees, and the employees spending money. But in general, $7 worth of value was added to the economy for every $1 spent on Apollo. And in modern space development, it is said, according to the National Space Society, that this return is even higher, where every $1 invested creates $40 worth of value. This isn't just an economic multiplier. This $40 comes from value added to other industries. So space tech that's used in other industries and downstream industries, and it generating more value or more efficiency there. In fact, the Aerospace Technology Institute found that the SROI, or the social return on investment, which this 40-to-1 figure is estimated at 70% per annum. So every year, $1 invested will bring back 70 cents, compared to a 15% return on normal Earth-based industries. To give an example of some of these industries, we can look at specific constraints that have to be accounted for in the environment of space. So firstly, obviously, we have to deal with the near total vacuum in space, and building for that has improved material science and sealing, which results in the ability for us to manufacture semiconductors using extreme ultraviolet lithography. Another example is the use of ionizing radiation. See, ionizing radiation can corrupt electronic devices, so we need more fault-tolerant logic. And as a result, this helps improve the safety of autonomous vehicles and other heavy vehicles, such as autopilots in aircraft, and pretty much anything that's autonomous in a growing digital world. We have thermal space, which helps us improve the energy efficiency of buildings on Earth, because we can design passive climate control systems that work in space, and then we can reuse them on Earth to reduce people's energy bills. We also have closed loop isolation, which is one of the more important ones. Obviously in space, if you're out of water, you can't just go to a dam or to a well and just fill up your bottle. You have only a certain amount of water on board. So this improves our ability to build circular systems, and those same circular systems can help improve resource resilience in areas like that are water strained, for instance. Finally, we have orbital debris and chaos. Obviously, there's a lot of satellites in orbit, and there's the growing concern of space junk building around in low Earth orbit, and this helps us improve our predictive kinematics. What that does is it improves our management ability for autonomous logistics in, for instance, high-speed drones, or air traffic control at an airport, or freight management, or even vehicles on a highway. Now, I just want to end on a quote. Many say exploration is part of our destiny, but it's actually our duty to future generations and their quest to ensure the survival of the human species. If we accept that space is the ultimate insurance policy for our species, then the talent pipeline is our most critical infrastructure. Every time a bright mind is lost to symbolic overflow or to rational choice theory, we fail in our duty. More than a luxury, this is our destiny. I'd like to thank the YSC organizers for hosting me. My name is Ashok Gupta, and I thank you for your time and attention.